All right, we are live. All right, welcome back, everyone. Thank you for joining us. It's a pleasure for me to introduce my colleague Flavio Bruno, also originally from Argentina, who's now based in Madrid, and he's an experimentalist working on ARPES of 2D materials, and today he's going to give us an overview of his work in the past couple of years. Thank you all for joining us. Flavio, please go ahead. The stage is yours.
Okay, thanks, Adrian, for the introduction, and thanks for inviting me to present and share my work. So my name is Flavio Bruno. I'm now based at Madrid, at the Complutense University of Madrid. And I will be discussing today about our results on the electronic structure of oxide two-dimensional electron systems. I'm an experimentalist working on ARPES, so I will be describing these systems from an ARPES point of view. That's why it's an ARPES overview. Because I'm not sure how familiar are you with these systems, I will make a brief introduction of 10 minutes to why these two-dimensional electron systems, why STO and KTO are relevant materials in this moment for the oxide electronics. So let's go ahead. This is not working. Yes. So first, let me acknowledge my collaborators, of course. As I said, I'm based here in Madrid, in Spain. Emmanuel Martinez is my PhD student, and Juan Beltran, it's a collaborator doing a lot of theory. I want to especially thank Siobhan McKeown-Walker and Felix Bamberger, which are in the University of Geneva in Switzerland, where I work until 3 years ago. And a lot of the experiments that I will be showing were done in collaboration with them. And we continue collaborating until today, even though we are not at the same place anymore. Of course, I want to thank all the people in the beamlines, in the ARPES beamline in different countries, in Diamond, the United Kingdom, in Switzerland, in Germany, because many of the measurements that I will be showing are synchrotron-based, although I will also be showing lab-based laser ARPES experiments. And finally, also the group of Jean-Marc Riscon that gave us some samples to perform experiments. Of course, let me acknowledge funding from the regional government of Madrid and from the Ministry of Science of Spain. So this is the outline of my talk. As I said, I will be first introducing the two materials STO and KTO that I'm going to be presenting results. I'm going to motivate a bit into what is the history of two-dimensional electron systems from an experiment point of view, and then I'm going to start really with the ARPES results. So for those of you who know the system, I apologize for this 10 minutes introduction. So potassium titanate and strontium titanate are both materials, are perovskite materials. One can think of, for example, on STO, of having a titanium atom surrounded by an oxygen octahedra. In the corners, we have the strontium. This is either cubic or almost cubic for both KTO and STO, but we can think of it as cubic for the purpose of this talk. It's commercially available as a substrate in any orientation, 001, 110, 111. So we can do a lot of experiments in a very reproducible way. Both materials are insulators. We know them from a long time ago. We can dope both systems, either by chemical substitution or by introducing oxygen vacancies. And they have a particularity that they can become metallic, or they become metallic at extremely low carrier densities. And this is very useful. So from this point of view, they are very similar, but there is, let's remind, I'm going to remind everybody that introducing oxygen vacancies is the tool that I'm going to be using to dope these systems. For each oxygen vacancy that one introduces, nominally, this is not fully true, but nominally one creates a 2+ localized charge and frees 2 electrons to move into the system. As I said, this is not true because the oxygen vacancies can move and part of the electrons are localized, but we can think of it as a positive localized charge and some electrons that are free to move. And the main difference between KTO and STO, which is the way that I'm going to be calling potassium titanate and strontium titanate in this talk, is that STO is a 3D empty band material, while KTO is a 5D empty band material. So the effective spin orbit coupling strength is much, much larger on KTO. So if one makes a calculation of the electronic band structure, one can see that the spin orbit coupling plays a major role in opening this gap between the bands, which for the case of STO is 20 milli electron volts, while for KTO is almost 400 milli electron volts. So we have to remember this key fact for the rest of the talk. So okay, so we know KTO and STO, which are the materials that we are going to be studying. Now, how this two-dimensional electron system field originated? Well, this happened now 20 years ago, almost 20 years ago, when this paper appeared by Harold Wan and Kiro Tomo, and they show that when lanthanum aluminate is deposited on top of strontium titanate, a two-dimensional electron gas appears in this very clean interface. This is surprising because LAO and STO are band insulators. And in this way, the pretty much celebrated LAO-STO field was born. Now, after this study, a lot of groups working on oxides starting to work on different aspects of this two-dimensional electron system. Just the excitement can be easily understood because two-dimensional electron systems in conventional semiconducting materials like gallium arsenide or silicon gave a lot of surprises, but one has to take into account that in the bulk form, the conventional semiconductors are kind of boring. Now, if we can make the same kind of two-dimensional electron gases or systems with materials like STO that are in itself superconducting, for example, one can hope to gain or to observe fascinating physics, which indeed was the case. So a few later after the discovery of this two-dimensional electron gas, for example, it was demonstrated that this two-dimensional electron gas is superconducting. After studying the properties of this system, people starting to try to create this two-dimensional electron gas in different forms. So for example, by ionic liquid gating, one can dope STO or KTO. Both materials is possible to dope in this way and to create a two-dimensional electron system. But not only with an ionic liquid, we can put different crystalline oxides, aluminum oxide, lanthanum titanate on top of the crystal. And again, we have a two-dimensional electron system with new properties. Very recently, for example, it was demonstrated on exotic orientations, let's say on the 111 orientation of KTO, that one can observe even a superconducting two-dimensional electron system on KTO 111. So you see the evolution goes from 001 STO to putting different materials on top, to using KTO, to using different orientations. So there is a lot of work, and by now, after 15, 20 years, these interfaces are really well studied. Not only that, but it's possible even to make devices. So in this case, I show an example of a field effect transistor using the LAO-STO heterostructure, and one can also create devices that are not possible to do, or that are not do not work so well with conventional semiconductors, like spin to charge conversion devices. In this case, using aluminum on top of STO. So you see, there is a lot of work on these interfaces, and a lot of work on the transport properties of these interfaces. So it's kind of a need for the field to understand the electronic structure of these systems. Of course, you can do this in two ways. You can do your first principle calculations. You can try to study to see where you have your defects, your surface relaxations. And indeed, this was done, and a lot was learned from this. Our point of view as experimentalists is to try to use a tool to measure directly this band structure. Now, in order to do this, what we use is ARPES, which we believe is an ideal tool to study these properties, because it allows you to directly map the electronic structure. So in one slide, ARPES works in the following way. We shine a photon into our sample, an electron gets kicked out. We have an electron analyzer. With the electron analyzer, we can measure the energy of the electron. Because we know how our sample is oriented, we know the azimuthal, we know the polar angle in which the electron is emitted, and by applying basically momentum and energy conservation laws, we can reproduce the electronic dispersion relation on the solid. So we know that this electron, when was on the sample, have such and such electronic dispersion relation, which is the objective of an ARPES experiment. And in this way, we can reproduce this electronic structure. Now, of course, this quantity, the dispersion and relation, depends on three momentum variables. So we cannot directly plot it. We need to fix some quantity. Because we do the experiment with one photon energy, the Kc component, let's say, the out-of-plane component of the momentum is fixed by this photon energy. Still, this is a three-dimensional object. So in order to plot it in an experiment, it's easier to show it as a two-dimensional graph. The way we do this is either we fix the energy, and if this energy is the Fermi energy, what we have is a Fermi surface map, or we fix momentum. And in this case, if we fix momentum, we have a dispersion plot. So in this way, this paraboloid is shown either as a circle, which is this guy here at the Fermi level, or as a parabola, which is this parabola, if we measure a cut at the fixed momentum. So using this tool, we want to study ARPES. We want to study the two-dimensional electron systems. This seems straightforward and easy because ARPES is an ideal tool. However, there is a problem with ARPES, is that when we shine photons onto our sample and we hit the electrons, not every electron gets out of the sample. The problem is that the electrons from deep into the sample scatter and do not reach our detector. Only the electrons in the first few nanometers go out and are measured. And that is why ARPES is a surface-sensitive technique, and we need extremely clean surfaces to perform ARPES experiments. There is, in fact, a so-called universal inelastic mean-free path for electrons trying to escape a material. And we see that at any photon energy that we use, we are around 5 monolayers of attenuation length. So we are sensitive to 1 or 2 nanometers on the top of our surface. Now with this caveat, let's see how we can use ARPES to determine the electronic structure of our two-dimensional electron systems. So I will start by STO001 because it's the most well-studied materials, and I think that is extremely good to illustrate the properties that we can measure to measure this system. So as I remind you one more time, STO, it's a band insulator. This is how the bulk electronic system looks like. We start in this experiment from an STO substrate, 001. It's clean, it's insulating. There is no two-dimensional electron system at this point. The potential across the sample is completely flat because we have a non-charged insulating sample. So what we do is we put the substrate, which is clean, into our ARPES setup. At low temperature, we shine light onto the sample. And the effect of these photons is to create oxygen vacancies in the surface of the sample. Now, these oxygen vacancies are created at low temperature at the surface of the crystal and are going to stay localized there, because the vacancies are positively charged. A downward bending of the potential is going to appear, and this creates, as you see here, a potential well, which is where the electrons are going to be moving and residing. This is like the cartoon picture of what we do. In order to prove that we are actually doing this, we measure the electronic band structure of this system. And in fact, this is what we observe. This is an actual measurement, and this is an actual calculation. This is not an schematic. This is an actual calculation. The colors are just put there to differentiate the bands, but this is an actual calculation that reproduces our measurements. What we see in the measurement is what we call the light bands, which at least you see 1, 2, and 3 light bands. This is the L1, L2, and L3, plus a heavy band, which is this one, H1 in orange. Now, if you compare with the bulk calculation, one first feature that is striking is that the degeneracy at the gamma point is lost. And it's not a small breaking of this degeneracy. This is almost 150 milli-electron volts. So it's a huge breaking of this degeneracy. A second point is that now we don't have only one parabola, but we have multiple parabolas. And indeed, this is the hallmark of quantum confinement. This is as when you put a particle in a box in your quantum mechanics course, and you have many quantum levels because of confinement. Here you put a parabola in a box. It's a box that it's a bit triangular, but it's a box still. And then the result is that you have many parabolas. So this is the proof number one that you have a confined electronic system. You have a second proof that you can do in ARPES, which is to measure the dispersion in the KC component out of plane. And if the system is really confined, it should not disperse. We did this. I will not show these results, but this is published, and you can actually measure the absence of dispersion in the perpendicular component. So there is a raised hand. Do you want to ask questions now? I don't know how is the protocol.
Okay, maybe
I'm happy. Yeah? I'm happy to answer questions in the middle of the talk.
Whatever you prefer. If you want to answer.
I think it's better if you do the question now. I'm going to try to keep the answer short, so we do not make it very long. But please ask the question.
Okay, thank you. So like this is a technical question. When you shine light onto the sample, does the temperature of the sample will be heated up during the measurement?
We shine the light with the sample at 10 Kelvin.
And does the sample will keep 10 Kelvin? Because normally the light can heat the sample, right?
But this amount of light does not hit the sample, at least not appreciable. So when you do any synchrotron experiment, you have a thermocouple that is constantly monitoring the temperature of your sample. These photons that I'm describing here, that I'm shining into the light, are the actual photons of the synchrotron beam. So it's not an extra light source. It's just the synchrotron beam. And in every synchrotron experiment, when you shine this light, you measure the temperature of your sample, and does not change appreciable.
Okay, I see.
So if there is a change, it's extremely small. Okay,
thank you.
So. So as I was saying, these many quantum levels prove that we have it's a first signature that we have a confined system. So what else can we learn from these measurements? So well, of course, let me say that we are not the only ones doing this type of experiments. There are 2 or 3 or 4 groups that know how to do this and have studied many aspects of these 2-dimensional electron gases. So we are not the only ones. So this is by now well-established technique to study this type of systems. But what else can we say? So let's see. This is the measurement that I was showing in the previous picture. Okay, let's see how the Fermi surface looks like, and let's try to understand, at least from a qualitative point of view, why it makes sense to have this band structure. Okay. So first of all, the Fermi surface that we have here on the top, you can observe that each of these parabolas gives rise to a circular Fermi surface sheet, okay? While the heavy state gives rise to this cigar-shaped Fermi surface that is very faint, but I hope that you managed to see, okay? So if you compare the quantum confined Fermi surface to the, this is a schematic of the bulk one. You see that the main difference is that instead of one circle, you now have many circles because of the quantum confinement. Okay, so this is the one aspect that we can understand of the band structure, is the reason of the many parabolas is the quantum confinement. There is a second aspect, which is the breaking of the degeneracy here. And in order to understand this, one needs to look at the bulk calculation, but this time with orbital polarization projections. So the heavy state here has dxy orbital character, which I plotted here. These are T2G orbitals, and the xy orbitals are in the plane. Whereas the other two states have a mixture of xz and yz components. In other words, they have an out-of-plane component. Now, the confining electric field is along the z direction. So what we see here is that a confining electric field along the z direction is going to drag down those bands that have a z component. And this is the reason why this band, which here is in the bulk is degenerate, it goes down a lot in the confined system. So, of course, this is an argument that we do with the hands, but the calculations also reproduce these arguments. One can even go and measure with ARPES the actual orbital polarization. We have done this. I'm not showing these results, but you can believe me or go and read the papers. But you can prove that the orbital polarization of these bands is indeed corresponding to this aspect. So okay, this is nice, but as our colleague was asking, this is done at low temperature in a synchrotron in an ultra high vacuum environment. So it's nice to make an ARPES experiment, but not very practical from a device perspective. So the trick that we want to do, or we wanted to study something that we can compare with an actual device in order to try to compute transport properties on this system and then go and measure ARPES. And the trick that we use is a trick developed in the group of Andres Santander Zero, which consists on, instead of shining light to create the oxygen vacancies, what you do is you put a thin aluminum layer on top of STO. Now, if you put aluminum on top of STO, there is a redox reaction. The aluminum wants to oxidize, and it sucks oxygen out of the STO. So effectively, it's creating oxygen vacancies in the same way as we were doing with photons. The advantage of putting aluminum on top of your sample is that you can put different amounts of aluminum, create different amount of oxygen vacancies, and in this way, you can observe that the size of the Fermi surface for increasing aluminum layer thickness gets larger and larger. So you can tune the density of your two-dimensional electron system by this method. Presumably, the band structure is going to be the same. The origin of the two-dimensional electron system is the same as in the photon irradiation. But now we can tune it and we can stabilize it in any value in order to study. Of course, there's a caveat. If you do this, you need to be careful when you do ARPES to not create more oxygen vacancies, because if you now grab this sample and shine high energy photons, you are going to change the density. And this is why this experiment is done with 6 electron volts light in a lab. At this photon energy, you do not change the density of your sample. We have tested this. These two-dimensional electron systems are stable for very long irradiation times. At this photon energy, this is important. So the second advantage of doing this experiment in a lab is that now the resolution of the experiment is much higher. The resolution in ARPES is, at least in momentum, it gets better as you go lower in photon energy. So at this photon energy, you can perfectly differentiate 2 bands here. And if you go to the highest density, you see 1, 2, and 3 bands. The gray plot here is a measurement of a sample on a synchrotron. So you see that on the lab is much sharper. The disadvantage of the lab is that at this photon energy, because of matrix elements effects, we are not able to see the heavy state. But this is because what you see in ARPES has a component that depends on the photon energy, but the fact that we do not see it does not mean that it's not there. The heavy state is there, it's just that we do not see it. Okay, but the big advantage that we are going to use is the sharpness of these light bands. This sharpness allows us to use calculations to test at different densities and to check if our model correctly predicts this electronic structure. So now what we do is we use a tool that we developed that is called BIMPO, that is basically an open source code that allows you to solve self-consistently for the confining potential and to find out the electronic band structure based on this potential. This is published here in arXiv, and you can download every file, and if you want to use it, please go ahead, and if you have any doubt, send us an email and we help you. When we publish a result like this, for example, if you go to this paper, you have every parameter to put as an input to the software to reproduce the calculations. So as I was saying, the advantage is that now we can compute for different densities and see that we can reproduce our measurements. This is important for us because this validates our calculations, and then we are going to use our calculations to make predictions that we cannot actually measure, but we trust these predictions on the band structure because these calculations are validated by actual measurements. This is a bit the indirect way that we work. This code BIMPO that we use, it's also allowed us to show in a very clear way that an idea that is used in the community, which is the so-called rigid band shift idea, is not correct and it shouldn't be used. Let me explain in one word this rigid band shift idea. It says the following. Because making many calculations for many different densities is costly in computing time and it's difficult, what people do is use one calculation for one Fermi level, for example, this one at 0, and then for a change in density, they just move the Fermi level without changing the electronic band structure. That's the rigid band part, and the shift comes from the fact that you change the Fermi level position. The problem if you do this is that you do not get the correct behavior you do not get the correct picture of your electronic band structure. In order to show this, what we do is let's assume that we use this rigid band shift idea in order to predict the distance between the light bands, what we call the Fermi wave vector for the first light band, which will be this point, and the second light band, which will be this point. In other words, I'm trying to measure this red arrow that appears here. So if I just move the Fermi level in this way, I move the Fermi level and I compute this distance, you see I'm putting the points here of the actual distance from the calculation as a function of the density. Now, if I do the actual experiment, which is this gray line, you see that the trend is not only that the values are wrong, the prediction of the rigid band shift model is that this should get larger, and in reality it gets smaller. So it goes even in the opposite way. So it gives you really wrong results to use this rigid band shift idea. Whereas if you use our model, which is the blue line, okay, you do not get exactly the right values, but at least you have a pretty good idea of the behavior of the system. You have the good trend, you have the good order of magnitude on this KF. And the same kind of effect can be observed for other quantities. The reason that we test our calculation with this delta K is that experimentally in ARPES, this is a quantity that we can determine with a lot of precision. So as I said, one more time, I want to remark that these tie-binding supercell calculations accurately reproduce our experiment, and then we can use BIMPO to predict new quantities that we cannot measure experimented. So let's move on to the Rashba effect in this oxide two-dimensional electron systems. How I'm going on time? Okay, half an hour. Okay, so I have 15 minutes. So this is the picture that I've been showing from the very beginning. If you look closely here, there is a splitting of the band that until now I have no describe at all. In fact, this splitting here is the manifestation of the Rashba effect on this two-dimensional electron system. This comes naturally in our calculation because the way that we do it is we start from a fully relativistic DFT calculation. So the spin degree of freedom is there. So when we put the confining potential, this splitting appears naturally. We do not need to impose any new ad hoc idea. This is extremely different, of course, to the picture of a Rashba effect in your non-interacting parabolic free electron gas. No, so the usual Rashba picture that we have in our head is just a parabola, appears an electric field, and we have a splitting in two parabolas, which gives two Fermi surfaces with spin momentum locking. So we see that the result in the oxide two-dimensional electron systems is completely different, and that is why we call this non-trivial Rashba effect. And this non-trivial Rashba effect is maximal in the points where we have an avoided crossing of the bands. Now, unfortunately, we try to measure this in ARPES. The way of doing this experiment will be to do a spin resolved experiments and to measure the actual spin polarization of these two bands. We try to do these experiments, but we do not have enough resolution on any machine until today. It's a mixture of the experimental side from the machine and from sample preparation that is extremely difficult to get a clean measurement. At least what we can say is that with the resolution that we have for this splitting, this is, for example, a comparison of the calculation and the actual measurement. So you see the measurement is extremely broad. So in fact, if we measure the spin polarization here, what you get is this line here, which is 0 because it averaged out. So because of the width of the measurement. At least what we can say is that the spin ARPES measurements that we did are consistent with our calculations, but of course we do not actually see the spin splitting. I just wanted to put this slide because there is a prediction of a giant spin splitting of almost 100 milli-electron volts that is completely inconsistent with our observations and our calculations. So in our opinion, this is the correct values for the Rashba. Now, luckily, we cannot measure with ARPES, but there was people in the group of Manuel Vives that make devices in which the result of the measurement on the device depends on the Rashba splitting. This is a completely indirect way of measuring Rashba. I'm not going to describe the experiment in detail. I'm just going to say that they have a two-dimensional electron system with a ferromagnet. They inject some spins, they measure a voltage, and from this quantity depends basically on the difference in the Fermi surface with one spin orientation and the other one. So from this value, they can deduce the sign of this and the sign and magnitude of this Rashba splitting. And what we did was to measure on STO the band structure. We cannot measure Rashba, we just measure the band structure. We validate our code. Based on this code, we can compute the Rashba splitting. And again, this is not a measurement, this is a computing based on our calculations of the Rashba splitting. And then they can measure the actual spin to charge conversion. And you see how the sign reversal and the magnitude of the spin to charge conversion really reproduces our prediction. So in an indirect way, we are confirming that our view of the Rashba effect on this case is valid. So it's a nice back and forth with the transport guys. So in order to say something different and to move away from STO001, let me describe a bit the two-dimensional electron system on 111 KTaO, which very recently became a really hot topic due to the observation of this superconductivity and anomalous transport experiments. There is a so-called stripe phase. There are many discussions regarding the transport properties of this system. So what we do with ARPES, as always, is to measure the electronic structure. So just to remind you, I already showed this slide before, but the feature that KTO, that potassium tantalate has, is this very large spin orbit coupling. So let's see what is the effect of this on the calculations and on the actual measurements. So this is the Fermi surface of 111 KTO. We see that it's very different to 001. This is expected. Now we are along the 111 direction. One has to think that all the T2G orbitals are equivalent. We don't have, as in the previous case, two orbitals with a component along the confining electric field. Now all three components, all three orbitals have a component along the confining electric field. And this is why we have a six-fold symmetric Fermi surface. Now we measure dispersion along these directions. First, along the gamma M direction, we have a heavy band and a light band here. Here on top, you have an MDC. And on the EDC that is taken at 0, I put it because you can see that you have this bumping intensity here, of course, but there is also a very faint bump here, which is the second subband. So we also have a confined electronic system on this KTO today. If we measure along gamma K, now there is two bands together. This is why it has a lot of intensity, this band, is because this in fact is not just one band, these are two together, as we will see in the next slide when we compare with our calculations. Again, these calculations are used with our code BIMPO. It's also useful for KTO. So you see that in this case, the difference between these two bands cannot really be resolved, and we see that the light state, sorry, the heavy state is this guy here along the XY, and the YZ, XZ are the heavy states, but this is completely equivalent. This depends basically on as you see in the Fermi surface, this is just these are all equivalent in the 111 direction. So it just depends on the direction that you're measuring. So we have a pretty good idea of how the electronic band structure looks like from experiment and from theory. Now, because the point of KTO is that it has a very large and Rashba effect, so we wanted to check if we were able to resolve it, but unfortunately we cannot resolve the Rashba splitting, but we can see what our calculations said about this Rashba splitting. So we compare KTO and STO to see if there is really an effect of an effect of this very large Rashba coupling. One can try to compare in the direction of maximal Rashba splitting, and you can do this. Here you have the values. Of course, you cannot compute the Rashba constant for the full Fermi surface because it depends on the point on the momentum space. So you have to calculate this quantity for each individual point. So we did this for the two main crystallographic orientations. Indeed, in KTO is larger than on STO, but we do not think that this is a relevant quantity from the point of view of a device, because if you make a device with electrons tunneling into this two-dimensional electron system, you cannot really distinguish between these momentum directions. What you are going to observe in your device is an average of the size of the Fermi surface for each spin orientation. So what we did is to compute the Latinger volume in KTO for each spin orientation and on STO, and you get that for KTO you have a 1% difference for each spin orientation, while for STO you have a 0.1%. So it is expected that if you make a device based on these materials, you should get an effect an order of magnitude larger if you use KTO, as long as the rest of the parameters are the same. So there are more parameters involved in devices, of course. Now, if you see the arrows that I plotted here, which are indicating the spin orientation of the outer and inner band, I only put arrows on these points, on the tips of the star, for a very specific reason. Is because these are the only points where the arrows are really tangential to the Fermi surface. If you move around the Fermi surface, in fact, you have that this spin orientation moves around a lot, and not only moves on the plane of the sample, but also has an out-of-plane spin component. This is a particularity of the 111 orientation. This do not happen on the 001. So if you compute the spin components of the vector, and again we cannot measure this, we can only compute it based on the calculations that reproduce our measurements. What you get is a threefold symmetry, which it's a 111 system, so we expect that with a threefold out-of-plane spin component. This is so far so good, and the idea will be how to check for this. And indeed, again, spin ARPES will be ideal, but there is no hope of doing this experiment because of resolution. But we team up with with the group of Panhi in Singapore, and doing transport experiments, they are able to deduce the presence of an out-of-plane component and the symmetry of the out-of-plane component. So they can, if you go and read this paper that I don't want to discuss because it's just a transport paper, but they are able to prove that they indeed have a threefold out-of-plane spin component in the 111 two-dimensional electron systems. So you see how the mechanic works is that we validate our calculations with as precise as we can do our measurements, and then based on these same calculations we can predict new quantities. And with this I'm reaching almost 40 minutes, so I'm going to stop here. I'm just going to conclude by saying that I have shown that ARPES is an ideal technique to study two-dimensional electron systems on KTaO and SrTiO. We can study basically any orientation. It's just an issue of preparing carefully your surface. I have shown that the electronic structure of this system have a non-trivial density dependence, which we can reproduce using BIMPO. So with this, what I want to say is that if you do calculations of these two-dimensional electron systems, you have to be careful. You have to do several densities to really understand the behavior of the system. No, it's not valid to just do one and rigidly shift your band around. And finally, I want to stress that this BIMPO code is useful because you can predict quantities like the Rashba effect, like orbital polarization, that are observables in some experiments, and that can be relevant for device fabrications. And with this, let me thank you for your attention. I led here the three references that I was mainly discussing in this seminar. Some time ago, we wrote a book chapter that is an extremely good introduction if you want to study this topic. Of course, it's from 5 years ago, so it's missing the latest results, but all the results are very well described there. So with this, if you have any question now, or if you later want to contact me, you can just Google my name or my email and let me know. Thank you. Now I'm happy to take questions if there are any.
Thank you, Flavio. I think I speak for everyone. An applause, I think this is a very fascinating talk, very interesting results. Now I want to open the session for questions. Please feel free yourself to raise your hand, or feel free to unmute yourself and ask a question.
May I ask a question?
Sure.
Something probably very simple and basic for you, but I have a question about orbital assignment of this heavy and light bands. Why can you explain easily why XY band is heavy band and XZ/YZ are light bands? In cubic system, XY, XZ/YZ should be equivalent. Now, in layered system, I would expect just the other way around, that at the surface, XY bands, XY electrons have very strong hopping along the surface. So I would rather expect that XY band should be broad and should be light band and not heavy. Why XY is heavy?
So if you go to the bulk system, of course, so let me go back. Let me go back.
It looks like in the bulking cubic system, X, Y, X, Z, Y, Z.
It should be the same. No, so it's so this is what you're saying is why this XY band, which in the
XY
cubics,
band is a narrow and heavy band. I
Yeah.
would rather expect that XY should be the broadest band, because that's actually gives you large hopping along the surface. XY hops electrons which are
XY hops along the
overlapping, so
surface.
hopping
Yes,
in X and Y direction.
exactly. So XY hops along the surface, and then when you confine perpendicular to the surface, this band is heavier than the YZ, XZ.
Why?
Uh,
That's the question.
Yeah. Now I fully understand your question. I don't think I have a. I don't think I have a. Huh. I will have to think about it. Yes, I don't think I have a direct answer now. I don't have an answer. I have to think about it.
It might be in principle that light and heavy, they have not much to do with this particular orbital character, because we know that, for example, even in simple semiconductors like silicon and germanium, there are also light, or gallium arsenide, there are light and heavy bands, but these have more complicated origin, not just simple XY orbital, for example, which is heavy. I would expect just the other way around, but okay, fine.
Okay.
Let's come to this.
So from the experimental side, all I can say is that we are sure about the which ones are light and heavy, but yeah, I don't know. Did I get confused? Maybe I don't know. Now I'm trying to think about this. This was done like 6 years ago. Did I put the labels wrong? I don't know, but hopefully not.
Maybe not. Maybe not, but I want to understand why.
Because now I'm trying to think about it.
Okay, very good. Yeah,
sorry, but I will try to. I find your email and I send you an answer.
Okay, very good. Thank you.
So. Yes, I was just writing down the question.
In the old days, it was said that photoemission measured bulk density of states rather than surface density of states. So near a metal surface, for example, the bands are narrower, or the density of states is narrower than in the bulk because they're fewest nearest neighbors, essentially. And it was said that with photoemission, you see the bulk density of states, you see bulk 3D momentum conservation, not just 2D. I know for something like this, your bands are localized near the surface, so there's no issue. And you're pretty sensitive to surfaces with that. But it's not like, say, grazing incidents or something like that.
No.
Yeah.
No, I was going to say that the confinement width that comes from calculations and other experiments is 2 nanometers, let's say. So it's 1-2 nanometers. So it's not the surface layer. It's confined. You can project the measurements. It's on the 3rd or 4th monolayer, but it's close to surface.
Okay.
Yes.
Do we have any other questions from the audience? So if not, let me ask you a question that's maybe a little bit technical. You may not have time to answer it right now.
Okay,
so
we can
let me
discuss
know
later.
Right. So in the case of spin ARPES, what limits the resolution?
So it's not an issue of spin ARPES even. It's just even in ARPES. Let me show you. This is the sharpest measurements that we have done, and I think it's probably the sharpest that has been published in oxide two-dimensional electron systems. So you can basically grab this measure at the Fermi level. So you see this line here, and you can try to measure the actual width of this line, and the width of this line is larger than the splitting that you expect in the case of Rashba. So the intrinsical width of the state is larger than the splitting, and this is not spin resolved ARPES. In spin resolved ARPES, the electron count goes much lower, and it's experimentally your bands are broader. Not because the system is worse, it's because experimentally the fact that you need to select the spin orientations technically makes everything broader. This is a technical issue. So it's an experimental issue. Also, there is an issue of sample preparation, because the width of this line, so this setup where this was measured, it's supposed to, so we have measured with better resolution, let's say. What is somehow saying that what is limiting this experiment is the surface quality. So if you have some defects on STO, it will create regions of different density. It will make, so let's say you have one perfect density, you will have a straight line in an ideal world with a perfect machine. But if you have defects around, you will have a slightly different densities, so your line will move around a bit, will make everything a bit broader. So this is a sample preparation problem, which we think it exists.
Yep. Got it.
So,
thank you so much.
The problems can come from different sides.
Mm-hmm. Perfect. Thank you very much.
So we are really trying. We really try a lot to measure. We really want to try to measure this spin resolve on this. We never manage.
Question?
All right. There's a question by Bob Markiewicz. Please, Bob, go ahead.
I thank you for a very nice talk. STO is very close to a ferroelectric instability.
Yes.
If you could make it ferroelectric, would things change?
Yes. So absolutely. In fact, there is some transport experiments. What they do is in the group of Manuel Vives, they dope STO, I will say with barium, or they dope with something STO to make it go through the ferroelectric phase. And in this, indeed, they observe changes in the transport properties. We never measure ARPES on this system, but from the calculations, I can tell you that the very critical parameter, the reason that these calculations are extremely difficult to do, is because the permittivity on this system is huge. So your confining potential depends hugely on this permittivity. And a small change in this permittivity changes a lot your band structure. So if you make it ferroelectric, it will change a lot the band structure. It will definitely have an effect. And it would be nice to measure, but again, you need to somehow dope the system, and then you will want to, of course, measure both ferroelectric orientations to see the changes. There are experiments along these directions of transport, but as long as I know, nobody did ARPES on this.
You can also turn it ferroelectric by oxygen isotope substitution, which doesn't dope the system.
It's true. It's true. There is, yes, it's true. This is another strategy to dope it with an isotope. This would be a good idea to try to do this experiment. Thanks for the suggestion.
All right. Any other questions? If not, then let's thank Flavio one more time. And
thanks.
Again next week.
My pleasure. See you next week. And if anybody has any question, then you can email me later.
Thank you.
Bye-bye.
Flavio, and goodbye, everyone.
So we keep in touch.